Everyone, my name is Tan Galing. Today I will present the part A and B for our lab introduction to digital logic circuit. So in part A, we are asked to investigate the logic gate operation. Okay, we are given 4 IC chip. Okay, and for the part A, for this lab simulation, we are still using the same QCS software to simulate all the construct and simulate all the logic circuit. So for part A 7402 IC result, we get the result that the LED light will light up when the input A and B are low. Okay, either input A or B is high, the LED will not light up. If both A and B are high, the LED light also will not light up, showing low in output. Then we identified that the logic gate 7402 IC is same as the NOT gate identity. Okay, the next one is 7404 IC. Okay, the result we get is the LED light will not light up even the input is high, showing the output is low. But when the input is low, the LED light up means the output is high. Then we identify this logic gate 7404 IC is same as NOT gate. So yeah, 7404 IC is a NOT gate. Next is 7432 IC. When both the input A and B are low, the LED will not light up. And when the input A or B are high, then the LED will light up, means the output is high. Okay, if the input A and B are high, the LED will light up, so the output is high. The identity of the logic gate 7432 IC is same as the OR gate. Okay, so we clarify it as a OR gate IC type. The next one is 7408 IC. The output, which is also the LED light, will not light up as both input A and B are low. If input A or B are high, then the LED will not light up as well, which means output is low. Okay, if both the input and A are high, then only the LED will light up, showing output is high. Okay, the identity of this logic gate 7408 IC is same as the AND gate, so 7408 is known as AND gate. And the last one is 7400 IC type. When both input A and B are low, the LED will light up, show that the output is high. Okay, when input A and B are high, the LED will light up, show the output is high. If both A and B are high, the LED will not light up, so the output is low. In fact, the logic gate 7400 IC is same as the NAND gate. Okay, and I have summarized it into the truth table of all the logic gate for different type, the 5 type of IC chip. Okay, this is the input 0, 0 means 0 stands for low and 1 stands for high. Okay, and next is part B. For part B, we are asked to use Boolean theorem to simplify the logic circuit and get the result of F. Okay, we use Boolean algebra and also De Morgan theorem to simplify the circuit and find out the output of F. And this is the truth table of F. Okay, this is the Boolean expression equation for output of F. Okay, that's all for my part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sadam Muda. I am from BEKM. My metric number is B012110161. Okay. Half edit is a combination for XOR gate and AND gate, and we must put label at the circuit like A and B, because we want put some number into table, like uh, I I put 1 in S1 and I put 1 in S2, so the result output 1 or sum become to 0 and output 2 or carry become become 1 for the result. Okay, it is a circuit for full adder and the table for full adder. I change output A and output B for the sum and carrier. Output A is a sum and output B is a carrier. Okay, we can approve the truth table from the K-map equation. Like S1 is a sum, so A and B, the answer is A, observe B, and process of C. So A from here, A, observe B, observe C. For the carrier, we use C out. C out is C carry. From here, we use output B. Okay, so equal A times B plus B times C in plus C in time A. So we can substitution. Okay, this is combination of adder and full adder. This one is half adder and this one is full adder. From combination of adder and full adder, we can use to calculate number, like I use 01 plus 11 equal 100. In decimal number, 01 is 1, 11 is 3, and 100 is 4. So I change all power source to uh, number, like this one is 0 and this one is 1 and this one and this one is 1. So the output is 100. This one to output C become 1, output B and output A become 0. Okay, this is addition and subtraction. This is a parallel circuit. So how I want use addition and subtraction? Okay, I must change all the power source to become binary number, like 0, 1, 1, 0, 1, 0, 0, 1 to make addition or subtraction. For the example, addition 2 plus 4 plus equal to 6. I must change all the number, decimal number to binary number, like 2 equal 0, 0, 1, 0, 4, 0, 1, 0, 0, 6, 0, 1, 1, 0. So 2 plus 4 equals 6 equal 0, 1, 1, 0. 0, 1, 1, 0. Okay, subtraction. 7 minus 5 equal to 2. Okay, in this situation, the circuit cannot calculate in minus equation. So, I must change 7 plus negative 5. Okay, so 7 is 0, 1, 1, 1. And negative 5 is 1, 0, 1, 1. Equal 0, 0, 1, 0. 0, 0, 1, 0.
Hello and a very good day to my lecturer, my fellow friends. My name is Divyan Rajkumar Sanam Balakrishnan, and today I would like to explain about my part, which is part D, flip-flops, subtopic to the part 1, which is the synchronous RS flip-flop. So now, according to the figure 5-1, you can see here that these RS flip using NOR gates, which is consist of 2 NOR gates. Okay, let's go to the quick simulation. So this is the circuit I have drawn for this part. And as we all look to the left, we can see that there's a 2 NOR gates, which is given the left shape. But I added another 3 lower gates, and I'll explain why I added 3 NOR gates later. Okay, so now let's focus on the construction of the circuit first. So since I already draw it earlier, so I would like to explain back how I construct the circuit. So first, I have gone to the components, I've clicked digital components, and I've select digital source and I drag it here. So I drag it to digital source. So then once digital source is been settled, then as I said just now, this RS flip-flop is using two NOR gates, so it's using NOR gates. So I select input no, and I drag it here, and I place here, and I will also place here as these three as well. Once I place these two NOR gates, I would like to state that the output of y1 is connected to the input of y2, whereas the y2 output is connected, it flow into the y1, giving the output of q and output of q bar. So then I also place another three NOR gates here, where three NOR gates here, which is connected from the y2 and y1, y3. So this is y3 and y4. Another one I connected, I draw another one here, which is the y is connected from here to the set. This is connected to the set. Okay, now I would like to explain the detail about the RS and synchronous flip-flop. So before that, make sure that you all label the wire label and label USD. So I label D set. I label um, I label reset as C. I labeled Q Y1 as Q and labeled Y2 output as Q bar. And also don't forget to name as set for the digital source and also reset. Okay. Now I would like to explain about the circuit, but before that, since it's a NOR gate, so I would like to have a reference, which is this, which is the NOR gate. So it's easy to me to make a reference or explain about this circuit. This is a flip-flop. So we can see here that when A input is 0, when a B input 0, the output produces 1. When the A input 0 and the B input is 1, produces an output of 0. And also when A output input is 1 and B input is 0, is produce 0. And also when the both inputs are 1, it also produces 0. So we can see here that the NOR gate only produces output 1 when it's A input and B input, both of them are 0. Okay, once, I hope you all clear about this. So once we all understand about this, let's make a reference for this RS synchronous flip-flop. Okay, now let's see here first. So okay, for D, which is set, the wire here is connected to the logic gate for Y5. So you can see here that this input of Y5 is actually 0. So actually 0. So once it's actually 0, it produces output of 1, which is like this. When the A output, when the both outputs are 0, it produces output of 1. So it's like this. Same as well. When the set input is connected flow from here, which is both of them are 0. So it produces 0, 0, it produces 1. So the one, which is the Y5 output, which is producing 1, is flowed through the input of Y4. Y4. So then the Y4 input, another one, it connected to the reset input as well. So we can see that here one, the Wi-Fi output just flow to the Y4, which is 1, and the reset input is 0. So 1, 0, it's 0. 1, 0 is 0. So as you all see here that let's say this is a reset output. This is the Wi-Fi output, which is 1, and the 0 is the reset input. So it processes when the set this one, 1 0, it produces 0. So that's why this is 1, this is 0, and it produces 0. Okay, then let's look for y3. y3, we can see here that the reset input is 0. It just connected to the y3 output, y3 gate, logic gate. So we can see here that another part is the set input is also connected to the y3, and the reset also is connected to the y3. So I can say that 0 0 is connected to 1. So we can see here the NOT gate. So it says then the A input and the B input 0 produces output of 1. So I can see here that when the reset input is here and the set input is connected, says 0 0, it's 1. So yes, 0 0 is 1, and here it's 1 0 is 0, and also it's connected to the y1 and y2, and also it will produces the output, which is not similar output. So we can see that it's let's say 0 0 1, it's 1, and 1 0 0. So I can say that if it's so 1, let's say 1, let's say it's 0 here. So when y1 output, let's say 0, is connected to the y2 input. So let's say just now it's y4, the output is 0, because it's 1 0. So if so, it goes to the y2 logic gate, which is 0. And as I said just now, the y1, let we just estimate that the y1 output is 0, because the y3 output is 1. So if it's 1, let's say it's 0, it's just connected to the go to the y2 input, which is 0. So 0 0, it produces a output of 1, q bar 1. And same goes for y1 logic gate. When the q bar is 1, it goes to the logic gate of y1, it flows, and once it reaches, so when, as I said, it's if it's 1 1, it produces 0. As we can see the logic gate, that's why I have the reference for logic gate, so for you to understand. So and I see here, this is as I said, this is 1. As I said, this is a 0, this is 1. So when it's 1, let's say its q is as I said, it is 0. When the q is 0, go to the y2, it's 0 0 becomes 1. And the y2 output, when it's 1, it goes to the y1 input, becomes 1 1 equals to 0. As I said, that's it. Yeah, and that's it. This for this. So after that, after we already explained about this, we have to get the timing diagram. So we need to save it, and you have to wait a second. So okay, once we have saved, and we have to stimulate it, so to get the timing diagram. Okay, now oops, okay, now we have to select timing diagram. You have to drag it. You have to paste it here. So the timing diagram, we have to what we need in the timing diagram is we need set, reset, q, and q bar. So this is C is for set, C for reset, D for set, q is the output of q, and q bar for this another output. So we click apply. Before that, I just want to make sure the solid line is a bit thick so that you all can see clearly and easily to refer. Okay, so okay, for that one, I want to double check to make sure it's all correct. So when I click apply, click OK, and oops, all right. Okay, then drag it. I just drag it to be wider so you all can easy to see. And this is the timing diagram that I have provided and obtained. So one more reminder, guys, if you all cannot obtain the timing diagram, which means we have that means there must be an error. So don't forget to place the digital simulation from the simulation, you can go and just drag it here, or you can just go to digital components, and we have another digital simulation here. We have alternative parts to select the digital simulations. So right, okay, now let's focus on the timing diagram. Okay, now this is the timing diagram we produce. Okay, why I choose 100 nanoseconds is because to make it sure it's understand. So we can choose any nanoseconds you want. You can choose 50 nanoseconds, you can choose 60 nanoseconds, because to make it easier to see how the waveform is flowing. Okay, right. Okay, now first of all, let's focus on C, which is the reset. So you'll be wondering why it's flowing in a square shape. So before that, previously I just reset the timing for 5 nanoseconds and 5 nanoseconds, which means that it will off 5 nanosec, it will on 5 nanoseconds and will off 5 nanoseconds. So that is the principle for this reset and set. So it will on 5 nanoseconds and it will off 5 nanoseconds. Okay, same goes for set as well. But I label it at 20 nanoseconds and 20 nanoseconds. Same goes for set. It will on 20 nanoseconds, and it will off 20 nanoseconds. Okay. Now let's explain what reset. For the first 0 to 5, you will in off state. You will be in off state, and once it reaches 5 nanoseconds, it became high state, and it will be in on state as well. So after it reaches another 10 seconds, after the range of 5 now to 10 nanoseconds is 5, so it will be on. But once it reaches another 5 nanoseconds, it will become off. So it's like this. It's operating in on and off operation. So this because it's off, so then it's operating on, so it's off again, it's an on and off again, it's on. So it's operating on and off every 5 nanoseconds. So yeah, so it's operating off in 5 nanoseconds, and it opens again for about 5 nanoseconds, and it's off again about 5 nanoseconds. Okay, assume it's like a push button, where for push button reset, you will just on manually, and you will off automatically. So let's say if I just push the push button, it will just on it manually, and once I just push it again, once I just release it, it will just automatically off. So same goes like this. That's how I explained for reset. It will just off and on automatically like that. But for set, when it operates, when it's on, it operates manually on and off manually as well. So you will on and off manually. Okay, let's see for D. Okay, as I said, I already set for 20 nanoseconds for set. Okay, for D, for the 0 to 20 nanoseconds, it's in off state. It's an off state, which means it is off state for 20 nanoseconds, and then once it reaches 20 nanoseconds, it will start to operate at a high state. So it will start to operate at a high state, which is 20 nanoseconds, and then you will off back again for another about 20 nanoseconds, and you will just off on back again for 20 nanoseconds. It's just like it is an off stage. So it will on about 20 nanoseconds, and it will just go off again about 20 nanoseconds. Okay. Yeah, it's off again 20 nanoseconds, and you will be on again about 20 nanoseconds. You will be off again 20 nanoseconds. Assume it's like a push button, as I said. Once I push it for reset, if I push it for reset, it will be on. If I release it, it will be off automatically. But for set, if I push it, the push button, it will on. But once I release it, it will be still in off, on. But when I push it again, you will become in off state. Yeah. So I say again, When set, when I push the push, and when I push it on the push button, it will become on state, and once I release it, it still will be on state. Once I push it back again, it will become off state. So that is for set. Okay, now let's go for Q. Q output always follow the set as well, so it's having this similar waveform. As you can see that the Q waveform follows exactly the set waveform, which is an offset. And once it is reaches the 20 nanoseconds, it will become in on state. So like this, it will flow on 20 nanoseconds when on state. When it flows, when it reaches another 20 nanoseconds, it will start to off. So you're operating in an off state. Then you will, once it reaches a 20 nanosecond and another 20 nanosecond, you will start to operate. And you will when it reaches 20 nanosecond, you will start to off, which is according it is following the same similar operations as D. Okay, whereas for Q bar, for this Q bar, it is really opposite compared to the Q. We can see here that when Q is operating in off state for the first 0 to 20 seconds, but for Q bar for 0 to 20 nanoseconds in operating in high state, and once it reaches 20 nanosecond, it operating in a low state, in off state. So it's really opposite that this really I can say that the Q and the Q bar is really opposite. So as I said here that okay 0 to 20 seconds it will in off state, and but when it reaches 20 nanosecond it will begin in a low state. So we can see it's really opposite the characteristics of the waveform. Hello here. And a very good day to my lecture, my fellow friends. My name is Divyan Rajkumar from Group 25, and today I would like to explain about part 2, which is the synchronous D flip-flop. So as shown in the lab sheet below, so this type of flip-flop is a 74774 positive edge triggered flip-flop. So what is a D flip-flop? So D flip-flop is known as data or delay flip-flop. So in here we have set a clock, a VCC, and ground. D is for data switch. So the D is synchronous, which means it's only synchronous with the clock, while set and reset is not synchronized with the clock. Okay, now let's go for simulation. So this is a simulation circuit I've drawn. So this is the D flip-flop. So for D and clock, I'll connect it with digital source. Same goes for reset. And for set, I've connected with logic state, which shows the 1 or the 0. And for Q, I've labeled as Q, which is the output for this. Okay, now done. Then for digital simulation, I've placed here and I've select time list to show the time diagram, and the time I've selected is 13 nanoseconds. So you can choose any nanoseconds you want. So I prefer 13. So now then we have to save the file. Then we have to simulate it. The simulation time sometimes takes a long time, depends on your laptop. So now once the simulation is done, then I need to provide the timing diagram. So I take in the timing diagram from the diagrams. So I need to choose clock, the input, the output, set, and reset. After apply, click OK. So now we click here. This is the timing diagram for the 5 o'clock, the input, Q output, S and R. So if you guys didn't look clearly, so I make it a bit darker and thicker. So this is the timing diagram. So you can see now it's a bit clearer as well. So yeah, okay. So now we can see that this is the time diagram. So when the D flip-flop is applied to the power, and the CLK is going low from 1 nanosecond to 3 nanoseconds, there nothing happened to the Q output. So only stays at low. And even though the D input is switch back and forth as well, like it switches and turn off and switch again and turn off. So for the output Q, nothing happens. It just stays in a low state for 1 seconds to 3 nanoseconds, because the D input is synchronous input that operates with a clock function or clock input. As I said, the D is synchronous with the clock. Okay, then after the Q is cleared by momentary pulse, the RST input load to 3 to 7 nanoseconds. So the D is set at high and the clock is applied with a negative going transition for 4 to 7 nanoseconds. Um, so to 4 nanoseconds, the clock is going to a negative going transition when the D is set high. Okay, then when D is 1, the output Q is remains low. So then the CLK input is changed to positive going transition from 7 nanoseconds to 10 nanoseconds. So then the output Q shows high when the C clock input changed to a positive going transition when D is 1. So when D is 1, the output Q shows high when the CLK input is going transition is a positive going transition. So after D input, the input became low, and the CLK input is pulsed momentarily from from 11 nanoseconds up to 14 nanoseconds or 13, but the output was cleared to 0 because the step was carried out from 10 to 11. So we can see here that from 11 to 13, the CLK was going a positive going transition, while the D is on low state and also Q on low state. A very good day to my doctor, Professor Abdul Rahim, and my fellow friends. Today, I would like to continue part 3, which is JK flip-flop. Okay, JK flip-flop is also known as Jack Kilby flip-flop, which has a synchronous and asynchronous input. So for today, in the lab sheet, you can see that this flip-flop is a 74L7LS IC flip-flop, or which is known as a negative going transition flip-flop, which consists of a clock reset, set, ground, Q bar, and Q, and also the data switch. So now let's head to the simulation, where this is the simulation of the JK flip-flop I was constructed just now. So for the JK flip-flop, we have two flip-flops here in the digital components, but we choose the JK flip-flop which has the set and reset. So this is the flip-flop we're gonna use. And so for clock, I label your clock, and we have connected with digital source. Say in K, I've connected with logic state, same goes for S. And for reset, I also connected for digital source. All these components you can take from digital components, which is here. You can take the digital source and also logic state. Okay, next, then we have to label we have to connect it with the components, and you have to label it using the wire label. Then we have to we have to place the digital simulation trends in here, and we have to select for time base for that to appear the timing diagram. So for time nanoseconds, I have chosen 100 nanoseconds for the timing diagram. So for reset, I've chosen 20 nanoseconds and 20 nanoseconds. Is because that so it will start to begin, or it will high state, or will be in start position for 20 nanoseconds and will go off for another 20 nanoseconds. So for clock as well, I chosen 5 nanoseconds as same. It will start it will be high state for 5 nanoseconds and will go off for 5 nanoseconds. Okay, then I would like to save this part and I would like to simulate. Okay, once the simulation process is over, so we like to obtain the timing diagram. So we choose clock, we choose reset, Q bar, Q and Q bar. Apply OK. So this is the timing diagram we obtained. So to make it, since it doesn't look clearly, so I would like to make it thicker, so it will be easy to look. So this is the time diagram I obtained when it is j equals 0, k equals 0, and s equals 0. So this is time diagram. And as we can see here, for the first 5 nanoseconds, the clock is in off state. When it reaches a 5 nanoseconds, it start to on, and it will be in high state when it reaches 10 nanosecond. So the range between 5 and 10 nanoseconds will be high state, and then once it reaches the 10 nanosecond, it will go off for another 5 nanoseconds. Then we will go on and off again, on and off again. So yeah, because it's set for 20 nanoseconds. For reset, for the first before 20 seconds, it will be now offset, and once it reaches the 20 nanosecond, it will be in higher state until it reaches 40. It will become in low state as well. So we'll be on and off for another 20 seconds. For Q bar, we can see here that it always appear in the high state, but before that it remains in don't care position. Same goes to Q bar, it at opposite, which is in low state. So now we also J and K we have been tested by using various logic states. We have been tested by when J equals to 1 and K equals to 1, or J equals 0, J equals to K equals to 1. So we will be tested a lot of um, uh, situations. So when J equals to 1, K equals to 1, the key output Q keep toggles, and also the positive Govan translation and the negative Govan translation is applied. At clock, you will remain previous, the Q will remain previous state. So that's for J equals to 1, K equals to 1. When J equals to 0, K equals to 0, the Q output will remain as high. You can see it like this. It remains at high, and Q, there will be no changes at the Q output when the pulse input applied as well. So that's for J equals 0, K equals 0. So when J equals to 1 and K equals 0, and we can see here that the output is going transition from low to high. So yeah, it's for J equals to 1, K equals to 1. Once J equals to 1, K equals 0, the output is going transition from low to high, which is it tends to change from low position to high position. So once when J equals 0, K equals to 1, the output Q will remain as low. The output Q will remain as low. So there's no changes at the pulse input. When the pulse is applied, the Q will remain as the Q output will remain as low as well. And yeah, when K equals to 1 and J equals to 1, the output Q remains as high, and since then there will be no changes when the pulse is applied as well. So when the J equals to 0 and K equals to 1, the output Q will remain as low, or it will remain as a low state, and so far, and then there will be no changes when the input pulse is applied. So when the J is 0 and K equals to 1 and S equals to 1, the output Q changes from low to high, which is the low state from the high state, and there will be no changes when the uh, input was applied. So it will be in tend to change from low state to high state. Okay, that's all there. Thank you.